Bismillahirrahmanirrahim. Welcome to the channel. My name is Asim Amjad, and in this video the learning outcome is to solve an elastic beam bending problem for the maximum flexural stress in both tension and compression. This is a typical bridge, and I am going to look at a strip of one beam and how much load it carries for a bridge. So I'm going to actually estimate it for this one beam span of 250 pound per foot, and this constant load in bridge structure is not insignificant and is a big part of the design. We will include an addition 350 pound per foot for the truck load, but it's not actually distributed. It's actually a point load, or a truck vehicle would be more distributed. So here's my structure, and I'm going to use a rectangular cross section type. And so to start with, we will look at other cross sections later on. I'm divide this video in two parts. In the first part, we draw the shear and moment diagram and determine where in this beam does the maximum moment occur, because that's what we want to design for. And on the second part of the video, we determine the maximum flexural stress in tension and compression and where it occurs on the cross section. So let's start with part A. First of all, we have to draw the reaction forces of the bridge due to different kind of sports and distributed loads. Here you can see the force AY due to this roller pin, and here you can see the reaction force By due to this pin type of sport. Here you can see three resultant force of the distributed load. How we can calculate the resultant force of F1? For calculation of resultant force of F1, simply multiply the force 250 pound per foot to its length, that is 35, and its total resultant force is 8,750 pounds. Same procedure is performed while calculating the other type of resultant force, that is F2 and F3, and these are the correct answers. So after drawing the free body diagram of the beam, calculate the summation of moment at point A, and here you can see the force By that is moving anti-clockwise, so it's a positive, as we consider the anti-clockwise moment are positive, and the total distance that is covered is 120 feet. Simply 35 plus 50 plus 35 is equal to 120. Then this resultant force is moving clockwise direction, so minus 8,750 times the distance, that is 17.5. As we know that under the UDL condition, the resultant force is applied in between of the distributed load. That's why the half of the distance would be 17.5, and the total distance of this section is 35 foot. Same procedure is repeat for the other resultant force, and then you come up with this reaction force By that is equal to 23,750 pound. After finding the reaction force of By, now let's find the reaction force of Ay. So we are now considering the upward direction of the force as positive. So Ay plus By minus these three resultant forces, then you would come up with this value of Ay reaction force, that is equal to 23,750 pounds. Then after calculating all these reaction and resultant forces, draw its shear force diagram, or SFD. You can say shear force diagram to SFD. So here you can see the reaction force is moving upward, so it's a positive in the direction, and the force is 23,750 pounds, so this is our starting point. Then you see the setting resultant force is moving downward, and this force value is 8,750 pound. Simply calculation of the setting point of the shear force for shear force diagram minus this force into this force. As this force is moving downward, so this force would be negative, and this force is moving upward, so this force would be the positive. So 23,750 minus 8,750 pound would become equal to plus 50,000. Then move to the next part of the beam, that is F2 resultant force, that is equal to 30,000 pound. So plus 50,000 minus 30,000 pound would become to minus 15,000, and we move to this point and simply draw a straight line here and a straight line there too. Then move to the third component, that is 8,750 pounds. Again simply minus this component into this force, that is minus 15,000 minus 8,750 pound would become to minus 23,750 pound, and then add this reaction force would become to 0. So after drawing the shear force diagram, move to the bending moment diagram. For drawing the bending moment diagram, we have to find the areas of these points. So the area of this rectangle is 5,25,000. As this left hand part is replica of this right hand part, so the area of this rectangle would be equal to the area of this rectangle. So this side of rectangle area would also be 5,25,000. Now calculate the area of this right triangle, and the formula of this right triangle area would be 1 by 2 times base time height, and the base is 35 feet and the height is 8,750 pounds. As this is the 15,000, so this height would be the 8,750 pound, and the area would be 1,53,125. Then same procedure is performed for calculating the area of these three right triangles. And then move to the bending moment diagram starting from the 0. First point is here, and this point value is 6,78,125 pound, and this value is come from summing these two areas, that is 5,25,000 plus 1,53,125, and the result would be 6,78,125. Then add this area to this value and you come up with this point, that is 8,65,625. Then minus this area, that is 1,87,500, and the result would be 6,78,125. And then again minus this area, and the final value would be the 0, and the slope is touched at this point. So all these slopes are parabolic in nature. So after finding the shear force and bending moment diagram, you clearly see the maximum moment force is 8,65,625. That would be the answer of the part 1. So the maximum moment would be 8,65,625 foot-pound at the center of the beam, that is 60 foot from the left edge. Okay, now let's move to the second part of the video. On the second part of video, we determine the maximum flexural stress, that is in tension and compression, and where it occurs on the cross section. We know that our rectangle length is 10 inches and its height is 25 inches. So this is are the neutral axis. So this point to this point length is 12.5 inches, and same for the 12.5 inches for the lower side. this side of the beam would be in compression and this side of the beam would be in tension. So we can find the maximum flexural stress by using this formula, that is sigma max is equal to mc or I. So the C from this figure would be equal to 12.5. For moment area, I is equal to 1 by 12 B times H cube. We know that the moment formula of the simple rectangular cross section from our previous video lecture. So plug in these value into this formula and then moment area of the simple rectangular cross section would be 13,020 inch 4. Then substitute these value into this sigma max formula, and as our values are in inches, so convert this moment value into inches by simply multiply to the 12 inches per foot. So this foot cancel out this foot and the answer of sigma max will be 9,972 pounds per inch square. For checking of this value, convert this value into KSI units. So the sigma max will be 9.972 KSI. And we know that the yield stress of the steel is equal to 36 KSI. As this value is less than this value, so our beam will remain in the elastic region. So this would be the answer for our said problem, that is sigma max is equal to 9.972 KSI, and this force would be in compression at the top of the beam and it would be in tension at the bottom of the beam. This is the three-dimensional graph of our said problem, which shows the maximum compression at top of the beam and maximum tension at bottom of the beam. Thank you.